Good afternoon, everyone. We're just going to wait a few minutes to let the crowd gather virtually. If you've only just joined, we're going to wait for a couple of minutes to start the webinar, because it usually takes people a few minutes just to get set and online. So I'm just going to wait a few more seconds, and then I'm going to introduce myself, and then anyone else that joined us a bit later will miss the introduction, but they'll get the good stuff. My name is Brian Wilkie. I'm the Vice President for Engineering for North America for US Microproducts. We are based in Austin, Texas. I've been with the company for about 7 years. You probably gathered that I don't originally come from Texas. I moved over from Scotland many years ago and desperately trying to hang on to my Scottish accent, which when I go back over there, people tell me I have lost completely. So in 7 years, I've been learning more and more about displays, but before that, I spent 25 plus years in the semiconductor industry. So, and when you get right down to it, as I'm going to explain in a few minutes, displays are just semiconductors that happen to be written on glass rather than silicon. So, let's get started. We're going to talk about organic LEDs and what's organic about them, and try and give you an overview of the fundamental technology in OLED displays. This is going to be a bit more technical than my usual webinars, but hang in there, because there's some pretty useful information, and it will make you better customers for us. So, here we go. We're going to start with an explanation on what are light-emitting diodes and how do they emit light. We're going to talk about why make them organic, and then we'll go into the different structures in light-emitting diodes, organic light-emitting diodes, the passive matrix stuff, and the active matrix, or AMOLEDs. Finally, we're going to talk about how to make them flexible, and we're going to end up with explaining why it's a pretty expensive thing to build customized displays in AMOLED technology. So let's look at a diode. Light-emitting diodes might emit light, but why? Well, first of all, a diode is the simplest semiconductor device. We start off with a crystal of pure silicon. On one side, we dope that or put in a contaminant that makes it easier for that side of the silicon to emit electrons, when we connect them up to a battery. On the other side, we use a different dopant that makes it easier to remove electrons from the device. And once we remove an electron, we call it a hole. It's something that positively is charged, and it will move around inside the silicon. So when you hear me talk about holes, what I really mean is a place where an electron would neatly fit back in if we would only supply an electron for it. But being positive and negative charges, those electrons and holes attract each other, and they end up meeting in that depletion layer, and the electrons drop into the holes to go back to a neutral state. And since the free electrons have higher energy than the electrons in the molecule itself, then energy is released. And the way that energy is released is as a pulse of light, a photon. And if the semiconductor is transparent to that color of light, and if it can be allowed to escape, it can be used as a light source. Incidentally, that same structure happens to let only current flow in one direction, which turns out to be useful. Problem is that most semiconductors are made from crystals of silicon, and those are pretty good in infrared light, but not much good in invisible light. So what we did was we developed more exotic crystals like gallium arsenide phosphor to output visible light. We started off with red light, and then we gradually got more and more exotic materials that would give us green and blue light. Problem is that those different colors require different crystal structures with energy gaps, the gap between the free electron and the captured electron being different, and the size of the energy gap gives you the color that's emitted. And that's all very well, but if we want to build colored displays, then we would need to use 3 different materials integrated into the one device. So making colored displays using regular inorganic LEDs is a really tough thing to do, although we're trying to do that with micro LED displays. More of that in another year or so. Anyway, they're also crystal materials, and they're not flexible, so not very useful for flexible displays. But if we go talk to our friends, the organic chemists, they can give us molecules that act very much like semiconductors. And by choosing different molecules, we can generate different colors of light. And I'm not going to try and go through what all those different molecules are, although I would like to mention that coumarin in there, which is very neat for green colors in your display, is actually a close relative of warfarin. So I'd advise you against eating your displays once you get a flexible display on your phone. Just don't eat it. It might not be good for you. Those materials, though, can be made to be transparent. They can be made to be homogeneous. They're all one structure. They're not. They don't depend for their properties on the direction that they're laid down in. They can actually be made more like plastics than small molecules, and depending on the display technology, we use them both ways. But they're okay in heat. They're pretty durable, and they're able to transport electrons. So they're a lot like semiconductors as it happens, but a lot more amenable to being tuned and chosen for specific colors. So how do we build an organic LED? We start off with a sheet of glass. We have to get the battery connected up to it. So we have an anode that's made of indium tin oxide, ITO. That's a somewhat metallic, good conductor that happens to be transparent, and it's used a lot in display technologies. We then lay down a hole injection layer, which is a bit like the one end of that diode, and so that allows the anode to take away electrons and create those holes. We use a different chemical to transport those holes up through the structure. Then there's a host layer, and that's the one where we choose a different chemical for a different color. So the whole injection, electron transport layers are all common, but each pixel has 3 colors in it, and each of those colors is a different host chemical. So on top of the host, we put electron transport and electron injection layers, different chemicals, and we end up with a cathode, which is a metallic layer on top of the whole thing. So we've built a diode structure. It happens to be built of organic materials rather than semiconductors, but it operates the same way. Electrons are attracted to the holes, and when they come together, the electron pops back into the hole inside the host material, and that has the right band gap to emit the chosen color of light. And that light goes down through those transparent layers, including the anode, out through the glass, and gives you a display on the outside. So pretty complex chemicals, but it ends up with being a nice, very nice, color tunable light source. So let's talk about how to build those organic LEDs into different devices. We're going to start off with what we call a PM OLED, a passive matrix organic light emitting display. And those are useful in small devices like fitness trackers and the like. And the way we build these is we take a glass substrate and we lay down strips of anode material, usually indium tin oxide. And so those will form the rows of pixels in the display. And then we put down red, green, and blue, or sometimes just white organic layers to make the actual light emitting part of the diode. And then we finish it off with a cathode, which is regular metal arranged at right angles to the anode. So that forms columns of diodes. So now we've got rows and columns of diodes that we can drive to emit light. What you do is you build many of these on a sheet of glass, and then we add some UV glue, and we put a cap on the back of the device. So you end up with glass, an anode, the organic layer that emits the light, and the cathode. And we cut those. First of all, we put a cap on the back of the device. One of the things about organic semiconductors is they're pretty sensitive to moisture, and the glue that we glue the cap to the glass can actually allow trace amounts of moisture to percolate through it. So we add a desiccant on the back of the device that sucks up any moisture that happens to come through, and it protects the OLED from any damage. And we end up with a passive matrix OLED. We connect a flexible circuit to it, and there we have a display device. So what we have is an array of diodes arranged in row and columns. The flexible circuit connects those rows and columns up to an external circuit, which has a RAM inside it where you store what you want to display. And we start off with the top row of the display, and we drive that low, and then we put a voltage on the on each of the columns, and by modulating the width of that pulse of current on the columns, we can decide how bright that particular diode in that particular row is going to be in the display. Once we've done that, we step to the next row, and we go to the next set of memory locations, and we display that information. So you step through row at a time until you've displayed all of the pixels in the device. You've got to be careful because you need to do that so fast that the eye doesn't see it, around about 50 or 60 hertz. And that limits the number of pixels you can put in this type of display. But it has some pretty nice characteristics. First of all, it's a nice simple structure. It emits light, and displays that emit light obviously don't emit any when you don't allow any current to fly through it, to go through it. So you get a very good angle of display usability. You can look almost at right angles to the display and still see whether it's lit or not. And you can manage the power consumption of the device by simply getting your engineers to allow for displays with fewer pixels. So it becomes a battle between the engineers who want the battery to last a long time and the graphics designers who want fancy displays. And so fewer pixels give lower power, and you can modulate how long your battery lasts that way. The other thing that's nice about it is that it only takes a few mask layers to define the number of rows and columns and the number of colors in the display. So it's relatively inexpensive to do a full custom display in this kind of technology. So that's passive matrix OLEDs. Let's step on to AMOLEDs, active matrix OLEDs. On this one, we start off as usual with a sheet of glass, but this time we lay down some transistor devices on the back of the glass. Those are called thin film transistors, or TFTs. And what we're essentially doing is defining a memory for each color of each pixel in the display. So those TFTs will accept information from the outside and memorize it for how bright that particular pixel needs to be. Then we lay down an anode, which is separate for each pixel and controlled by that TFT matrix. And then we put down the organic layers that we usually make up an OLED with. And then we finish it off with a cathode that covers the entire area. So it's called a common cathode design, and each of the anodes controls how bright that particular pixel needs to be. So if we take a cross section through this, what it looks like is a multi-layer structure that we gradually deposit layer by layer, starting off with that thin film transistor. And then we put down a planarization layer that just levels everything off again. Then we put down the anode. We surround that anode with a spacer that separates each pixel optically from the next pixel, and an insulator that separates that anode from the next pixel so that each pixel is individually controlled. And then we put in the same hole injection layer, hole transport layer, the emissive or host layer that decides what particular color that pixel is going to be, and then the electron transport layers, and finally the cathode. So now we've got an individual pixel that we've decided which color it's going to be, and we have a memory to drive it. So this is just a summary of what I've just said. The trick with this technology is that those layers of the OLED are deposited where each color is deposited using what we call a shadow mask. It's essentially a very finely patterned device with a hole in it where a particular chemical needs to be deposited. And it's also important that we have that passivation layer on the top of the whole thing to keep that nasty moisture out of the device. To do that, we use something called vacuum thermal evaporation. We essentially boil the material in a vacuum and attract it over through that shadow mask onto the glass substrate that has the device in there. And each shadow mask is different. Some of them put down the overall hole transport material, for instance, and then some of them do one color and then the next color and the next color. So lots of process steps, lots of different chemicals required to put this all together. But what you end up with is an emissive display. So it's got all the advantages of the blacks are really black and the lights are really light. It has a very high dynamic range because the blacks are so black. If there's no current, there's no light. Whereas in an LCD, you're using the liquid crystal to act as a shutter to stop the light from the backlight getting through. And they don't make perfect shutters, so you don't get as high a dynamic range. You also get a very wide color gamut because you've carefully chosen the chemicals in the host layer to give you very blue blues, very red reds, and very green greens. Like the PM OLED, you can manage the power consumption so that the fewer pixels that are lit up gives you lower power. And lastly, it has the benefit of being flexible if you're careful about it. So let's look at how that looks in pictures. First of all, wide color gamut. Your steak on an AMOLED is going to look brighter, more colorful, much easier to see whether it's well done or rare on an AMOLED. The high contrast ratio, many times more than you get with an LCD, gives you very good detail in the picture. You also get extremely fast response time. An LCD can change the image in something around 20 milliseconds or 20 thousandths of a second. And the AMOLEDs are 100 times faster than that. So fast moving displays, things like gaming displays, are really nice on AMOLED. And finally, modern LCDs are pretty good for the viewing angle, but the AMOLEDs are really, really good because the light is being emitted directly very close to the surface of the display itself. So pretty nice technology, and where we're headed now is let's go and make those flexible. And it turns out that that's not particularly easy to do, but it can be done. What we need in the case of a flexible AMOLED is all those same layers as we have in the standard AMOLED. You've got the protective encapsulation, the cathode, the OLED stack itself that moves the electrons and emits the photons. You've got the grid that separates the pixels, the anode, and the TFT that forms the memory, and all of that on a substrate that's flexible. And so you've got to design all of these layers to be flexible, and that's not an easy thing to do. So the way we actually do it is we start off as usual with a sheet of glass. We lay down a polyamide film on top of the glass and then a buffer that allows us to build those thin film transistors. We build the transistors, we put in some contact holes, and then we add the anode. But this time we use a different material for the anode because indium tin oxide, ITO, is not very flexible. So we use, and I apologize for the typo there, we use something called graphene, which is a very thin layer of carbon atoms. And it's a pretty good conductor, and it's also flexible. So good stuff. And then we lay down the OLED materials, the same multi-layer structure as we typically use for OLEDs, and then end up with a passivation layer that protects the whole thing. But we've still got it connected to glass. So what we do is we hook up the flexible circuit that's going to connect the display to the outside world, and then we use a layer to pop the glass off of the polyamide, and then we throw away the glass. It's just been a carrier to keep everything on the same plane while we do that complex structure of multiple layers of transistors and chemicals. And we throw away the glass and we're left with a flexible display. It's pretty neat technology. So let's go to talking about why is it expensive to do these things? Well, the early TFTs used something called amorphous silicon transistors to form the memory on the glass, and that only uses about 4 or 5 photomasks. It's still in that technology is still in use today, although more capable displays typically use something called low temperature polysilicon, or LTPS, and that uses more mask layers, but it gives you in return much faster transistors. And to send lots of information in a complex display, you need fast transistors. So now we're up to 5 to 12 photomasks, and then we have to have those shadow masks that define the colors. And let me just go to the next picture. We start off with a fairly open mask that sets up the whole emitting layers and the whole transport layers. And then we have to go through 3 different steps, one for each color, where the gap in the mask is pointing to a different pixel. And then we end up with the cathode and the electron layers on the top of that. So multiple shadow masks to allow for the different colors and devices. And when you couple the multiple masks that you've got to design with the very expensive equipment required to use those masks, you end up with something that's that's really expensive to customize. But if you're building things in very high volume, or you choose a display size that's already being built in very high volume, then they're still pretty attractive displays. In fact, if you look at the market for AMOLEDs, in 2019, it was under $1 billion. By this year, we're expecting that to almost double. And you see the split there between TVs, which sell relatively fewer displays, but they're big, and mobile devices with much smaller displays, but very nice volume with them. And we expect by 2025, this market will be something like $2.5 billion. So that's why people are building factories to build AMOLEDs. It is worth finishing off maybe with just a description of the differences between LCDs and OLEDs. An LCD display is multiple layers. It needs a cover, a reflector, a light guide, optical sheets, LEDs for the backlight, and then two polarizers, one at the front and one at the back, a liquid crystal array in the middle built on thin film transistors, and a color filter. So it's a pretty complex structure that builds LCDs, but the technology is well understood, and it's relatively inexpensive to build LCDs. OLEDs, on the other hand, are very few layers. The majority of the magic is in the OLED array itself, and that's built in that very expensive factory using those very expensive masks laid down on glass, usually with one polarizer and a back cover. So it's a pretty simple mechanical structure. It can be very thin and very light, which is great for portable equipment. But customizing it and building it in those very expensive factories means it's relatively more expensive on a per display basis. And if you look at the technology, LCDs use that backlight. The backlight is on all the time, whether you're displaying anything or not. So the power consumption is relatively high, although the cost is relatively low. The efficiency is high on an AMOLED because you don't have that backlight that's on all the time, and the AMOLED wins out on higher contrast and the ability to go flexible, and it also wins out in the color gamut. And there's a standard for the color gamut you see on your television, and AMOLED can exceed that. So that's pretty nice. And they're also very fast, good for high motion. So that's AMOLED technology for you. Let me tell you a little bit about US Microproducts, and then we'll take questions. So why Usmp? We don't just design displays, we develop and deliver displays for demanding applications. Lots of our stuff goes in pretty nasty environments, and we do more than 200 display designs a year. So we're good at engineering displays to meet and exceed the demands of our customers. We've been around for a long time. We're in our 26th year now. We have a design methodology that we use to keep things in sync between our team in Taichung, Taiwan, and our team in the US that's directly supporting our customers. And we can be a great partner for your engineering team to build a great product in multiple different technologies, not just OLEDs, but TFTs also. So with that, I'm going to say, okay, let's take questions. So John is asking, in the host layer for each hole, approximately how many molecules go into each hole? Is it a certain volume or a clump of molecules? Actually, what we do is it's defined by the size of the pixel. So what you do is you optimize the molecule size and the thickness of that host layer around the size of the pixel and the pixel pitch in the display. So it varies for each color, and I'm not sure that I can give you an exact answer. In fact, I know I can't give you an exact answer, but we choose the pixel size, and then we optimize the thickness of that layer for the best efficiency in light emission. So, and why the heck do we have a polarizer in there? Is the question from Jerry, and the answer is the polarizer is there so that light coming in from the front of the display is cancelled when it reflects back out, so that you don't get external light robbing contrast from the display itself. So, are there any standard available sizes for OLED panels in the range of 8 to 12 inches? Yes, I believe there are, but you should contact our sales team, and they'll get down into the details on that one. Okay. Next question is about why I didn't emphasize passive matrix OLEDs. They're simpler, and they're relatively inexpensive. The problem with passive matrix OLEDs is that they don't do well above something like 250 by 250 pixels, because they're driven in a multiplex mode. Each row is driven at a time. So the reason that you would use an AMOLED is for a larger pixel size of display. If you want a fairly small display, like a fitness monitor, there are all sorts of smaller displays that only need to display a few characters or some simple icons, and they do really nicely in PM OLEDs. And we actually sell a lot of PM OLEDs. So it's just that the technology steps forward from PM OLED to AMOLED, and once you understand one, it's easier to understand the next one. So I was not deliberately dissing PM OLEDs. We like those things and be happy to talk to you about specific applications. So Chuck is asking, what's the lifespan of AMOLED versus LCD? That's a tough question to answer. Usually the lifespan of an LCD is measured in thousands of hours, and it's actually defined by the LEDs in the backlight will gradually get dimmer over the space of 5 or 10,000 hours, and if you're looking for a long life LCD, then you have to carefully choose and manage the LEDs in the backlight, because we quote the lifetime of those LEDs in terms of how many thousands of hours does it take for the light output of that LED to drop in half. AMOLEDs, the lifetime is defined by how good the passivation layers are on the back of the device, and they're getting pretty darn good at that these days. And the best witness to that is that the automotive industry is beginning to use AMOLEDs, and they're looking for 5 or 10 year product lifetimes. So unless they were happy with the ability of the AMOLED guys to deliver really good passivation, then they would not be doing that. So now you're going to have to go do some math on how many hours is a car driven a week over a 5-year lifetime. And I used to know that answer, but I don't think I do anymore. Okay, I have another question. Is it Anuj? Is asking. We're saying that polyamide is used as a substrate, and why are we using that? Is it the only substrate being used in the industry, or are we seeing the use of things like PET films? And the answer is that each manufacturer has different PET sets of layers that they use, and processes are optimized for that. And I think most of the usable substrates have been tried. You need something that's very stable in sunlight, because lots of these displays are used outdoors. So the question is it flexible enough without being too flexible, and will it stand up to the rigors of the outside world well enough? So there are, and how will it do for hardness as you subject your display to the rigors of ordinary life and the scratches and so on. And glass is pretty hard, and I don't know about you, but my watch has some significant scratches on it already after a couple of years of use. So the answer is that we are trying lots of different substrates, and from manufacturer to manufacturer, you'll see differences in the chemistry and the layers that they use. Okay. Taylor is saying you mentioned the passivation layer requires moisture countermeasures. How do they handle prolonged hot and humid environments? So the couple of different answers for you there. A lot of the R&D in the AMOLED business is focused on how to build passivation layers behind the device that are strong, flexible, long-lasting, and really good at keeping the environment away from the from the working chemicals in the front. And like I said, the automotive industry, which is pretty good at testing stuff, seem to be moving towards OLED displays. So I think you're able to give the kind of lifetimes, and we do test things in high temperature, high humidity environments, but we get lifetimes that seem to be pretty good these days. On the PM OLED side, we can actually customize the lifetime by customizing the how hard the display is being driven and how much desiccant we put inside each device. So we can actually manage that. Okay, I am running out of time and voice, so I'm going to answer one more question, and we'll get back to you with answers by email over the next few days. So I'm being asked, do we make flexible displays? Yes, we do have that technology available. I'd say that it's expensive and just coming to the point where we're comfortable with it in industrial environments. One of the challenges with particularly with AMOLED technology is that they are building them for consumer devices, and those consumer devices have relatively short life cycles. And it's only now that we're getting to AMOLEDs and later flexible devices that will be available in the kind of lifetimes that our customers expect us to be able to provide things. So drop us an email and we'll get back to you with what the availability looks like. But we're kind of at the leading edge of that availability. Okay, I'm going to stop and thank you for hanging with us through that relatively complex presentation. Please contact myself or our sales team if you've got other questions, or if you've got projects that you would like to have us take a look at. We'd be happy to work with you. So thanks, and have a good rest of the afternoon.